I want to talk today about putting electrons into the orbitals for atoms with more than one electron. And what I've done here is I've listed the different orbitals in an atom in order of increasing energy. So for n equals 1, there's only L equals 0. You can see that I've got, for n equals 2, I've got the L equals 0 and the L equals 1. And in a multi-electron atom, it turns out that the lower the L value, the lower the energy of the orbital. So 2s is lower than 2p, and so on. 3s would be lower than 3p, which is lower than 3d. If we add electrons to our shells, we can, or our orbitals, we can look first at a 1 electron atom. Let's suppose we're talking about a neutral atom like hydrogen with 1 electron. We can put it in the lowest energy orbital, and when we have it in the lowest energy orbital, in the lowest energy configuration, that is called the ground state for that. If we were to put it in a higher energy orbital, we would refer to that as an excited state. So the lowest energy electron configuration, is the ground state. Anything higher in energy is an excited state. We use these half arrows, by the way, to represent electrons. When we look at an atom with more than 1 electron, what we end up doing for the ground state is filling the orbitals in a way that we put in the electrons in the lowest energy position. So the 1s orbital can hold 2 electrons, and we draw these with opposite directions, these arrows, to represent the plus 1/2 spin and the minus 1/2 spin. According to the Pauli exclusion principle, we can only have 2 electrons in the 1s orbital. So if this were helium, both of its electrons would be in a 1s orbital. If I put in a third electron, it has to go into the 2s orbital. I can add a second 2s electron, and then I can, if I'm filling these in order of increasing energy, which is called the aufbau principle, I would add the next one here. Now we actually have something of a choice for adding the next electrons. There are a couple of ways I could do it. I could, since these are all equal in energy, which is what we call degenerate, I could add the next electron like this in one of the other degenerate orbitals with a parallel spin. I could add it in one of the other degenerate orbitals with a opposite spin. I could pair the electrons up with opposite spins. I couldn't pair them up with the same spin, because if I did that, that would be giving them the same m sub s value, and that would violate the Pauli exclusion principle. It turns out that there's a rule, it's called Hund's rule, which describes the energy of electrons in degenerate orbitals and how we fill them. And according to Hund's rule, what we do is we fill the degenerate orbitals individually before pairing up the electrons, and we put the spins in parallel. So for the 6 electron atom, I would have the configuration like that. For a 7 electron atom, I would have it like this. And now when I go and add my 8th electron, I would start pairing the spins again.